for the seminar. Yeah, exactly. Now, allow me to
Okay.
introduce you. Welcome
Yes.
everyone in this John Conway Spirited Seminar Series. Today we have the honor to have Professor Andrea Solotar with us. She is distinguished professor at the Department of Mathematics, University of Buenos Aires, and currently under the administrative role. We have the honor to have her because one of the reason is she is the director of the Commission of the Developing Countries from the for International Mathematical Union, and she received her PhD from Buenos Aires, and she's very well renowned researcher in the area of algebra. Particularly, her research interest lies on the boundary of algebra and topology. And today she is going to discuss something really very interesting about the conjecture, about Hans
Yeah.
conjecture, and that uses some specific type of cohomologies. So,
Mhm.
thank you, Professor Andrea, for accepting our invitation. And over to you now.
Thank you very much for the invitation. It's a real honor and pleasure for me to speak in this seminar. And we are also connected because you have several activities that are related with the activities of CDC of IMU. So I hope this will continue like this. And I know that you are trying to do a really a very good job. Okay, so today I started with, I will talk about a subject but it's of course algebraic, but since I know that it is, the audience is a broad audience, I will try to start from scratch so that I hope that you will all follow, and I will try to present some, in fact, two different conjectures. One is Hans conjecture, as in the title, and another one is a older conjecture that is called Nakai's conjecture. And I have been working on Hans conjecture during the last years, let's say several years, with my collaborators. I can mention Claude Sibils, who is a former director of SIMPA, and Eduardo Marco from Brazil, and Marcelo Lacerota from Uruguay. Well, we have been working on Hans conjecture, but I will explain our work in the end. Okay? So the first thing I would like to mention that we all know very well are vector spaces. Of course, vector spaces, you all know that they appear they are necessary when we are looking for the solutions of a finite set, or there is a type of linear homogeneous equations with coefficients in a field. So K is going to be a field for us. So sometimes the set of solutions of this homogeneous set of linear equations has certain symmetries besides being the solutions of that system. And we would like to take into account these symmetries, okay? For example, sometimes we may consider the action of some subgroup of the group of permutations on the set of n elements that we call Sn. It has an action on the vector space over K of dimension n, which is acting on the vectors on a given basis. So, for example, acting by permutations on the vectors of the standard basis. And then we would like to look at the set of the solutions of the given system, the originally given system, which are also invariant under this action, okay? So, for example, some symmetric solutions, okay? So, all these facts leads to considering linear equations with coefficients in a ring or in a K-algebra instead of considering linear systems with coefficients in a field, which is the easy situation. So if this is the case, we are looking at Kn, the K vector space of dimension n, not as a vector space, but as a module or representation of a ring. For example, in the previous case, it will be the ring K, the group ring of Sn, the permutations of n elements, okay? So, of course, we all know that all vector spaces have a basis, and this is not true when we are talking about modules over sorry, I have to change the bar. Okay, this is not true for modules. Okay, not all modules have a basis. Okay, so of course, this fact causes a lot, really a lot of problems because having basis is really very, very comfortable. So the amount of problems caused by this fact depends on the ring we are working with, okay? So for example, when we are working with a ring A, we are considering A modules, and the ring A is a principal ideal domain. Then we have a structure theorem for all finitely generated modules. So this theorem is available, and it describes completely the structure of these modules, the finitely generated modules, as a direct sum, as you know, of copies of the ring plus the torsion, okay? And there is a unicity in the number of copies of A and in the description of the torsion. So this is very convenient. This is a very nice structure theorem. And one instance of this is, for example, the existence of the Jordan form of a linear map on a finite dimensional vector space, okay? So this is an example of the importance of this structure theorem, where now we are looking at the vector space, not as a vector space, but as a module over the ring of polynomials in one variable with coefficients in the field K. Okay, but this is all very well-known thing, but we are going slowly towards our aim. Okay, so of course, we know that free modules are those modules that are, let's say, similar to vector spaces because they have a basis, okay? And since they have a basis, free modules are really much, much easier than other modules. So, of course, not all A modules for an arbitrary ring A are free, but given any A module, one tries to approximate it with free modules. So this is the main idea we have when we are trying to construct a resolution, what is called a free resolution of a module. So in fact, what is a resolution? And this is in the basis of homological algebra. A resolution is a collection of A modules, let's call them Li, together with some morphisms that modules that we will call Di. In particular, D0, we will call it P because it will be a projection. And we ask this collection of modules to satisfy the following conditions. The second condition is the one I just mentioned, that is that P is a projection, it is an epimorphism. And the first condition is that the image of di plus 1 is equal to the kernel of di, and this for all I. So in fact, it is an exact sequence, okay? So the idea, of course, is that since we have a module and a module M, which is maybe not free, maybe not easy, instead of considering the module M, we are trying to replace it by a sequence, an exact sequence of free modules, okay? The problem is that sometimes this exact sequence may be infinite, an infinite one, an infinite number of terms which are non-zero, and this is not nice. But we can think of it as if we were splitting the difficulty of the module M. Instead of having a module M, which may be difficult, we have a lot of free modules. Each of them is easy because it's a free module, but we could have a lot of them, maybe. And all the difficulty of the module M is going to be found in these maps that are called the differentials, okay? So it's like, instead of having a big problem, well, we will prefer to have several, or maybe a lot, smaller problems, okay? Please feel free to interrupt me if you have questions, okay? So this sequence here in the upper row, let's say, is what we call the free resolution of M as an A module. So let me mention that I am never saying it, but we have to choose, well, for example, I choose working with left modules, okay? Okay, so let's go back to solving, let's go back to school, let's say, which is the meaning of solving a linear system of homogeneous equations given a matrix, okay, given by a matrix. So, you know, to each system of equations, homogeneous, you can associate a matrix. So we have a matrix which is of size P times Q, okay? So computing the solutions of the system given by this matrix, in fact, corresponds to finding the kernel of the linear map induced by this matrix, by multiplying by this matrix, as we can see here. So in this way, we obtain an exact sequence of vector spaces, of K vector spaces. So with T, we go from K power Q to K power P, and we have an inclusion, we have the kernel of this T, the kernel of this T is inside K power Q. We can think, well, in fact, there is a monomorphism, but we can think that it is inside. And the number of copies of K that we have here is the preceding Q minus the rank of the matrix, okay? Minus the number of linearly independent equations, okay? So we can think about a homogeneous system of linear equations as a short exact sequence of, well, of course, since we are with vector spaces, all the vector spaces are free, they have bases. So now, let us suppose that the coefficients of the equations are no longer in K, no longer in a field, but suppose that, for example, they are in a polynomial ring, so in any other ring. So let's think about the example of a polynomial ring in n+1 variables. Then the kernel of the linear map T will not necessarily be a free module, okay, a free module over this. Even if we can use the Hilbert basis theorem to be sure that the kernel is going to be a module which is finitely generated, right? Has a finite system of generators. So trying to find the kernel, in this case, is trying to understand the relations among the generators of this kernel, okay, of this finitely generated module. But since this kernel, in this case, is not necessarily free, so we have a space which is going, well, we have a module which is going to be the space of solutions, but this space is not free, so we will need to describe maybe the relations among the generators, and then to find a finite set of generators of this space, and again, study the relations among them, and like this, continue taking kernels and successive kernels. So it's kind of replacing the kernel that for a vector space was free by a free resolution of the kernel, okay? So let me continue. So as I was saying, we are trying to construct a free resolution of the last model, the one to which we have the projection, which is going to be the co-kernel of T, okay? It's similar, is analogous to finding a free resolution for the kernel, okay? If we have one, we will have the other. So summarizing all this, finding the solutions of a system of equations with coefficient in a ring is the same, or is this procedure that is similar to finding a free resolution of a module, in this case the cokernel, over a ring, okay? A module over the ring, in this case the cokernel. Okay, so as in the same way as we think about vector spaces as solutions of systems of linear equations, we can think about free resolutions of module in a similar way. Okay? So, of course, I was saying that free modules are really easy, the easiest one, because one of the most useful things about free modules is that, of course, one has a basis, so denote our free A module by L, and denote by X a basis of this free module, okay? So a nice property of a basis is that if we have just a function from the set, the basis, to any other A module M, so it is a function because X is just a set, it's the basis, then we can extend this phi to a morphism, capital Phi, with domain equal to the module L with the one with basis X. And this capital Phi will be extending the previous function to the whole free module, okay? It's exactly the same thing that we do when we are dealing with vector spaces. We define a linear map on a basis, and then we extend it to the whole vector space. So, in other words, or in a diagram, this fact allows given modules N1 and N2 and an epimorphism from N1 to N2, each time we have a linear map or an A-module morphism from L to N2, we can lift it, we can find a map A that is going to be here from L to N1, such that the composition of beta with this A is going to be equal to the given alpha. So in other words, what we are saying is that given any map from L to N2, we can lift it to N1. So we are saying that the functor taking the homomorphisms of A modules from L to, well, here is the variable, maybe N1 and 2, is an exact functor, okay? It is always exact on one side, but the lifting property is telling that it is exact on the other side too. Okay, so we come to the definition of projective modules. Any question up to here?
So far, so
Okay.
good. I think projective module up till now it's okay. I hope. Is
Okay,
there any
okay.
question from the audience? So, okay, move on.
Okay, thank you. So I'm trying to start smooth in a smooth way. I hope. Well, it's not. I hope it's interesting. Okay, so of course you know that projective models. A model is projective if this functor is exact. So in particular, we were saying that free models are projective, and another characterization that we know of projective is that a model is projective and only if it is a direct summon of a free model. So some well-known examples of projectives. So for example, if our ring is K set 2 with K a field, 2 is with characteristic different from 2. And so, well, we take two idempotents. These are orthogonal idempotents, so we can write one also as E0 plus E1. And so we can decompose our ring as a direct sum of the left multiples of E0 plus the left multiples of E1. So each of them is projective and it is non-free. This is a very standard example. And the second one for, well, set modulo 6 well, we can decompose it as a sum of set 2 plus set 3, which is, of course, each of them is a non-free projective model. So there are several results about projective models that are quite useful and interesting. Let me mention what is called the Serre-Swan theorem, stating that there is a one-to-one correspondence between what? On one side, the finitely generated projective models over the ring of coordinates of an affine variety. So our ring is a commutative ring now. And on the other side, the vector bundles over the variety, okay? So this is a very, very interesting theorem relating finitely generated projective model, let's say algebraic objects, with vector bundles over the variety, which are more geometric objects, okay? And it is a very important theorem. Another result of this type is when the ring A is either a principal ideal domain or a commutative local ring, then we know things about finitely generated projective models, because in these cases, finitely generated projectives are always free. So, for example, if we were in the previous case, it would be a trivial band, okay? The previous statement, the second statement, I mean, is also true when we have K, a field, and we have the ring of polynomials in n variables for some n with coefficients in this field. And this is a theorem that has been proved by Daniel Quillen and Andrea Solotar, okay? So the idea is always trying to characterize finitely generated projective model, okay? Another instance of this kind of theorems is when we have a commutative in a Therian ring, we have a finitely generated A model, then one can prove that being projective is equivalent to being locally free. Okay, we are in a commutative, in a Therian setting, so we can localize, okay, in, for example, the maximal ideals, in fact, the complements of the maximal ideals, and being projective is the same as being free for each of the localizations, okay? So, in particular, we have that if you have a commutative ring and a finitely presented A model, we know that it is projective if and only if it is locally free. Okay, so we are very, very interested in dealing with finitely generated projectives and, if possible, describing them. And why are we interested in them? Well, because we need not only free resolutions, but projective resolutions. So we know that any A module, any arbitrary A module, has a projective resolution because the category of A module contains free objects, and free objects, we have already mentioned that they are projective. But the problem is that having free resolution is sometimes, well, free resolutions are sometimes very, very big. And when resolutions are big, I mean, the modules are really big, with a big basis, then it is very, very difficult to make computations, okay? And all the point of homological algebra is being able to compute invariance, okay? So let me mention, for example, a case where the free resolution is really too big and it's not necessary to have such a big resolution. So our ring is going to be a direct product, in this case, of two copies of a field K. And the module is going to be just one copy times the zero vector space over K. So we have already mentioned that for this type of modules, well, they are projective. And suppose that we are just looking, we say, well, we can deal only with free resolutions. And so suppose that we are looking for a free resolution of M as module over A. So in this case, we will have an epimorphism, of course, from A to M, that is a projection onto the first variable and then 0 in the second one. But it will have a kernel, we have to study kernels, and the kernel will be the second variable. And we want not just the second variable, but we want to cover it with a free model. So we need again the whole A. And again, we will have a kernel which will be a copy of K, but we need to cover it with a free model, so we need again A. And like this, just taking kernels of the projections and covering them with a free model, we find an infinite exact sequence, except here in the last one, because here we have the epimorphism to M. And this sequence is, as I was saying, quasi-isomorphic to M via the projection. And this resolution, this infinite resolution, even if each of the free models is of rank 1, it is very big because it is of infinite length. It never stops. But we have started with a model which is projective. So why would we need an infinitely, why would we need a resolution of infinite length? Okay, if M is already projective and we are interested in projectives. So in fact, what we are looking for is having not only free resolutions that may be too big, but projective resolutions that are as small as possible. And what do I mean by as small as possible? I mean, I have my zoom bar here. I mean, what are called minimal resolutions, okay? So what are we talking about when we say minimal projective resolutions? Okay, minimal in which sense? Well, of course, they are projective resolutions. So it's a sequence of modules with differentials such that no direct summand of pi for each I is contained in the kernel. So we do not have, let's say, submodules that we do not need to construct the resolution. We are not having useless models, let's say. And the length of a minimal resolution, for example, in the previous case, the length was 0 because the model was projective, is an important, very important invariant of the module, okay? But the problem is that such minimal projective resolutions, sometimes they do not exist, okay? So when do they exist? Well, as I was saying, not always. But if, for example, we have A, which is an Artinian ring, and in the case of an Artinian ring, we have a Schmidt theorem about writing models as direct sum of indecomposables in a unique way up to isomorphisms, then in this case, all finitely generated A model will have a minimal projective resolution, okay? So this is a very good case, and for example, it happens for finite dimensional algebras, okay? And when we have minimal projective resolutions, or in general, when we have projective resolutions, we can talk about the projective dimension of a model, okay? The projective dimension of a model that we are going to denote like this, we are talking about A models, is by definition the minimum of the length of the projective resolutions of the model, okay? So if maybe it is infinite, maybe not. And if we have a minimal projective resolution for M, then the projective dimension is going to be the length of this minimal projective resolution, okay? So in this case, we can just look at the length of this resolution and have the projective dimension. And then there is another invariant, but in this case, not of the module, but of the ring, which is called the global dimension. And the global dimension is going to be the supremum of the projective dimensions of the A modules. So for example, if we are talking about left A modules, then this is going to be called left global dimension. If we have right A modules, it is right global dimensions. For some rings, these dimensions do not coincide, but for Noetherian rings, they coincide, and we can be very comfortable, let's say, when speaking about global dimension. Okay. Why? Yes. Sure.
Professor Andrea, so the global dimension of a ring, what did you say in the Noetherian ring? This is the same as the projective dimension?
No. I said that for Noetherian rings, it's the same if we talk about left global dimension or right global dimension. Okay.
Mm-hmm.
And so even if we distinguish, if it's not commutative between right A modules and left A modules, this invariant is going to be the same, but not always if the ring is not Noetherian. Okay.
Okay, and in the case of Artinian structures, so all Artinian are Noetherian, so the answer will be the same.
Yes, it is the same. Okay. And this is, well, my rings are going to be, the rings I will be dealing with are going to be Noetherian and in many cases Artinian, and so I'm just going to speak about global dimension. And I am speaking about global dimension because it's related with Hans' conjecture in a way we are going to see quite soon. Sorry, I have my title, which is in Spanish. I changed everything, but not the title. Let me mention that the global dimension in some cases is 0. But as I was saying, this is a property of the ring. And this property of global dimension being 0 is equivalent to A being a semi-simple ring. Okay. So in this case, all the projective dimensions of finitely generated modules are going to be 0. Okay. In other words, all module is finitely generated is going to be projective. Okay.
Professor Andrea, what is the definition of semi-simple ring?
It's a direct sum of simple ideals.
Okay.
So in another example is when A is a principal ideal domain, so I'm talking about the commutative situation. Well, here, since, well, the name is because all the ideals are generated by one element, okay? I can find one element generating each ideal, and in this will make the global dimension of A to be smaller or equal to 1, okay? Since submodules of projectives are going to be projective, and so the resolution will stop at most in the second module, okay? So if it stops in the first one, the module is projective, then it is global dimension 0. If it stops in the second one, for some module, it's global dimension 1. So what happens in the next example? We are going to take A as a polynomial ring in n variables with coefficients in a field, and M a finitely generated A module. So M, the module M, will have a minimal projective resolution, which will be in fact free, because again of Hilbert's theorem, and the ranks of the free modules appearing in this resolution will be very well-known numbers in geometry, let's say, that are called the Betti numbers of M, okay? I'm not going to give details on the Betti numbers because they are a dimension of some geometric objects, but what I mean is that these dimensions are known from another point of view. Okay? Okay. So let me go to the following example, which is a ring of polynomials with complex coefficients in the variables t squared and t cubed, which is isomorphic to a quotient of a polynomial ring with complex coefficients in two variables divided by the ideal generated by this polynomial. Okay? And suppose that we take m equal to this ring divided by the ideal generated by x and y. In this case, if we work a little bit and we construct the minimal projective resolution of m, is going to be of infinite length. And thus, in this case, the global dimension of the ring A is going to be infinite. Okay? We are going to see next that the global dimension of A being infinite is related to the fact that when we are in the commutative case, like this one, the variety, the corresponding variety, that here it is a curve, it has a singularity. Okay, here we have a cusp, and so we have a point 0, 0, which is singular, and this is related to the global dimension being infinite. Okay, so as I was saying, the last example corresponds to the coordinate ring of what is called a variety with singularities, or a singular algebraic variety. When I say variety, it's an algebraic variety, okay? So in general, a variety is said to be regular if and only if the global dimension is finite. Of course, this is a homological definition of being regular, and it's not the usual one in commutative algebra, because the usual one for variety, for let's say a surface to be regular, a variety to be regular, is that if one localizes in each maximal ideal, then the ring we obtain has to be a regular local ring. And being a regular local ring has a definition in terms of the Krull dimension, okay? Being the Krull dimension being equal to the embedding dimension. So for example, if we are in the previous case where we have a cusp like this, we have the point 0, 0, which has two tangents, the tangent space has dimension 2, but our variety is a curve which has dimension 1. So this is a singular point because the dimension of the tangent space in the point does not correspond to the dimension of the variety. Okay? So this concept of being regular is related with not one but two well-known conjectures that I'm going to mention. One is Nakai's conjecture, this is older, and then Hans' conjecture. Just to know when should I stop, because I have not looked at the time when I started.
Still we have 10 minutes, 10 to 15 minutes.
Thank you very much. Perfect. Okay, this will be fine. So let me first mention things about Nakai's conjecture. Nakai's conjecture states that, suppose that we have a commutative ring, okay? And EFT stands for essentially of finite type. What is essentially of finite type? Well, being of finite type, we know what is in commutative rings is being a quotient of a polynomial ring in a finite number of variables divided by an ideal generated by a finite number of polynomials. This is of finite, being of finite type. Essentially of finite type means that maybe we have something that is not exactly like this, but each localization is of finite type. So each localization is a localization of a quotient of a polynomial ring by an ideal generated by polynomials. Okay? So Nakai's conjecture says that if A is such a commutative K-algebra, and we know that the ring of differential operators on the algebra A, the ring of differential operators, since we have derivatives and we have multiplication by polynomials, is a non-commutative ring. So here we are talking about a non-commutative ring, even if we started as a commutative algebra. So if we know that the ring of differential operators is generated by derivations, then Nakai's conjecture says that the ring has to be regular. Okay, regular in the geometric sense that I have already mentioned. The converse of this statement, that is that if A is regular, then the ring of differential operators is generated by derivations, is a result, a classical result by Grothendieck. Okay, and the conjecture is known to be true in some cases for a field of characteristic 0, and it's really a very small case, which is when the variety is a curve. And then there are some other cases where it is true in dimension 2 for a surface, and this is mainly due to Mount and Villamayor. These are very old results, but I like them because they relate the global dimension with the ring of derivations. And now the other conjecture I would like to mention that is related to global dimension is the conjecture that is known as Hans conjecture. And the conjecture says that if the Hochschild homology, what is the homological theory that is associated to any associative algebra, if this homology that is indexed by the positive integers is 0 for large enough, or I have an E, which is too much, is degrees, then the global dimension of A has to be finite. Okay, again, relating the finiteness of the global dimension with a homological invariant like the Hochschild homology, which is, of course, a derived invariant. And this conjecture has attracted a lot of attention in the last, let's say, 15 years, and it is known to be true for several families of algebras. For example, commutative algebras, essentially a finite type. But in fact, the problem, what we could call Hans conjecture for commutative algebras, has been solved a long time ago, before even the moment when Hans stated his conjecture. And it was studied a long time ago because it is related with a famous theorem which is called the Hochschild-Constant-Rosenberg theorem. And let me mention what is the Hochschild-Constant-Rosenberg theorem. And yes, suppose that we have an, not yet, I'm going to explain it in a moment, but suppose now that I have an algebraically closed field, and we have a ring, as I was mentioning before. Well, the geometric idea of regular, as I mentioned, is that for all maximal ideal in A, when we compute the dimension of M divided M squared, it has to be equal to the crude dimension of, and here I should say the localization of A in M. There is an M missing. Okay, so this is very commutative because we are talking about maximal ideals, full dimension, etc. But Jean-Pierre Serre proved that the ring A is regular in this sense, being commutative. Well, this condition being regular is equivalent to the global dimension being finite. So, as I mentioned before, this motivated the definition of regular in the non-commutative case, because we are no longer depending on maximal ideals, full dimensions, etc. Okay? So this is the definition of regular or non-singular that we are considering. So let me mention a very well-known fact. Well, you all know what is a derivation from an algebra A to a bimodal M. Okay, so map satisfying this. Why am I mentioning this? Well, because when A is a commutative ring, we can consider the module, what is called the module of scalar differentials, denoted like this with omega 1. And it is defined as the quotient of the free module with basis, the derivations, by the ideal generated by the relations that are here. Why is this object important? Because it turns out that the derivations, the k-linear derivations of A to M, from A to M, is isomorphic, or canonically isomorphic, to the A-linear maps from this module of scalar differentials to M. So omega 1 is important because we are kind of linearizing a problem. We pass from derivations, which is not linear, to morphisms, which are nicer, let's say. Okay, so now we can state Hochschild-Kosten-Rosenberg theorem from 61. It says that if K is a perfect field, for example, let's say characteristic 0, and A is a ring which is essentially of finite type and regular, for example, we can say that the global dimension is finite, then the exterior algebra on the module of scalar differentials is isomorphic in each degree to the Hochschild homology of A. So in particular, since the thing that is on the left is 0 for a star bigger than the rank of omega 1, then the Hochschild homology is going to be 0 when the star is big. So this is what I was saying, okay? The reciprocal statement, yes. Yes.
Professor, what is the Hochschild cohomology?
The Hochschild cohomology is let's say something very vague, is the homology theory that is associated to associative algebras in the sense of the operas. But in a concrete way, you can define it as the derived functor of the Tor functor over the ring A tensor A opposite, okay? So it's the derived functor of a Tor, okay? So it's a homology.
Whether this homology does make sense for commutative structures or not?
Yes, of course, yes. It's both for commutative algebras and for associative algebras that are non-commutative, okay? It's for any kind of associative algebra. So in particular, in case A is commutative, there is a very nice decomposition of the Hochschild homology. So on one side, we have this exterior algebra on the omega 1. This is one of the summons. And on the other side, we have what is called the André-Quillen homology, which is more specific to commutative algebras. And in the middle, we may have other things. Okay?
And what do you mean by essentially finite?
Essentially a finite type is that locally it is a quotient. It is like a quotient of a polynomial algebra divided by an ideal generated by a finite number of polynomials. Okay?
Okay.
Yes, thank you. So in particular, as I was saying, well, if the global dimension is finite, the Hochschild homology will be 0 for large enough degree. But if we look at the reciprocal statement of this, meaning that if the Hochschild homology stops, then the global dimension is going to be finite, this is exactly what is known as Hans conjecture. So in the commutative case, the Hans conjecture was proved already in 1991, This is Abramov and Biguet that prove it for arbitrary fields, I mean fields of arbitrary characteristic. And this is what a group in Buenos Aires that I was part of it, is the Buenos Aires cyclic homology group, that and we prove it for characteristic 0. Okay. And there is also a cohomological version. Okay, if we can say that if the Hochschild cohomology stops is 0 for large enough degrees, the Hochschild cohomology is also a derived functor of an on functor, then it's because the global dimension has to be finite. Okay, so for commutative algebras, it works both for homology and for cohomology. In the non-commutative case, for finite dimensional algebras, and if we are in an algebraically closed field, and we have a finite global dimension, then we know that the Hochschild homology is going to be 0 for large enough degrees. So there is an n missing here. I intended to say that in an article published in 1988, and a German mathematician, Dieter Happel, wrote that he did not know if the reciprocal statement was true or not, which is similar to the one I mentioned for the commutative case. But in fact, this is both by Greens, Madsen, and Solberg. Some years later, in 2005, I think, there was a counterexample, and the counterexample is these algebras, which are non-commutative. So Q is an element in the field, which is not a root of unit. And these algebras have finite Hochschild cohomology, but infinite global dimension. Okay, so it was a counterexample. And so just after this, I will finish soon because it's late, Yang Han proved that for these same algebras, the Hochschild homology was infinite dimensional, and the non-zero in infinite many degrees. And so he stated the conjecture saying that if A is a finite dimensional K algebra and the Hochschild homology of A is finite dimensional, then the global dimension has also to be finite. And he stated it and proved the conjecture for algebras which are finite dimensional and defined by monomial relations. And from this time, from this moment up to here, other cases have been proved. For example, for graded local algebras, for Koszul algebras, for some algebras that I don't know very well that are called graded cellular algebras, all of these in characteristic 0. And well, the proof is a bit complicated. And then for what are called the quantum complete intersections, that are algebras non-commutative of this kind. And then I prove together with Michelin Biguet for graded local algebras in arbitrary characteristic and some generalizations of these quantum complete intersections that are not necessarily finite dimensional. And then it was proved also, I proved it with 2 co-authors for generalized bialgebras. And then Berg and Madsen proved it for trivial, what are called, I'm not going to enter in the detail, trivial extensions of self-injective algebras. And then what we are trying to do with Sibils, Marcos, and Lancilota is to given an algebra, verifying if it satisfies Hahn conjecture by first making the algebra simpler. So our point of view is, if you have to prove the Hahn's conjecture for a family of algebras, first try to get simpler algebras for which Hahn's conjecture verified will be equivalent to Hahn's conjecture verified for the original algebras. This is our way of attacking the problem nowadays. And I think my time is over. So I would like to thank you very much for your attention and your questions. Thank you very much.